Years ago, men were seeking the philosopher's stone that would turn common metals into gold. They searched, too, for magical formulas like the elixir of life to cure all sickness and make men immortal. These early predecessors of our chemists were called alchemists, and their profession, if we can call it that, was alchemy. Some of the alchemists conducted experiments, but their procedures were crude, so very little of lasting value has come down to us from their work. Alchemists were often bewildered by the outcomes of their experiments, but such outcomes are easily understood by modern chemists. One of the founders of modern chemistry was Joseph Priestley of England. He lived at the time of our war for independence. Many discoveries have perpetuated his name, but one of his most famous experiments was conducted with a simple piece of equipment, a large burning glass. With the glass, he focused heat from the sun's rays on a tube containing some red powder floating on mercury metal. The heat, red powder. Priestley discovered that a gas had formed as the red powder decomposed. He tested some of the properties of the gas. He was thrilled to find that a glowing ember held in the gas burst into flame and burned with unusual intensity. He had discovered one of the most important gases in nature, but it remained for a Frenchman to offer an acceptable explanation of Priestley's observations. It was Antoine Lavoisier who repeated Priestley's experiments and conducted others. He sealed some tin and air inside a glass flask and measured the total weight. Then he heated the flask containing the tin and air for several hours. A coating of white powder formed on the surface of the tin during the heating. Lavoisier reasoned that the tin must have combined with something out of the air that was in the flask. If so, there should be no change in the total weight. To check his reasoning, he again weighed the flask and found that the total weight had not changed. Lavoisier explained that oxygen, an element from the air, had combined with another element, in this case tin, to form a compound. This combining of an element with oxygen is called oxidation. Only a few elements were known in Lavoisier's time. Today we know of nearly 100. Here in this periodic table, the elements are listed. Each element has a symbol, like O for oxygen to stand. In this table there is much information, such as the relative weights of atoms of the different elements. Teachers and technicians of today have a vast store of chemical information and experience to guide their work. And the young people of today are learning the fundamentals from which may emerge new chemical discoveries tomorrow. To them, each new chemical experiment is a further step in learning to apply chemistry to practical problems. Every chemical compound is the product of a chemical change, and chemical changes are involved in most chemical work. The experiments of Priestley and Lavoisier involved such changes. Here is another striking example. The instructor has placed some iodine crystals in a porcelain dish. Next, he adds a piece of another element called phosphorus. When the two elements, iodine and phosphorus, are brought together, a chemical change occurs. The compound phosphorus iodide forms. This compound has characteristics that are different than either the phosphorus or iodine used originally. Problems about the compositions and uses of substances have led to specialization in chemistry. Here are three important fields of specialization that have developed. Inorganic chemistry originally dealt with the chemistry of minerals. Organic chemistry originally referred to the study of plant and animal products. today the scope of these fields has broadened. Physical chemistry deals with the physical conditions of chemical change and with descriptions of these changes. All three fields of specialization rely upon the chemical techniques of synthesis, decomposition, and analysis. Let's look at some applications of chemistry. Synthesis, for example, takes place when two or more elements react to produce a compound, as in the iodine and phosphorus experiment. Synthesis may also take place in nature. Minerals are compounds formed by synthesis. To release the iron in this ore, decomposition, the opposite of synthesis, has to take place. In this smelter, such a chemical decomposition is going on. The metal is being separated from the ore. Chemists have different methods of decomposing a compound. The instructor is demonstrating a method using an electric current.
I have these two tubes filled with an acid solution. It's a common kind called hydrochloric acid. Now, the electrodes in the tubes are connected with a direct current power supply. And when the current is turned on, Phil, would you mind turning that current on, please? The tubes fill up with gas, like that, because the current decomposes or breaks up the acid solution into its two elements, hydrogen on this side and chlorine on this. You can see that each part of the U-tube is filling with gas at the same rate. That's because the hydrochloric acid